In this video, we're going to explore balancing chemical reactions. Remember that in a chemical reaction, the way in which elements are combined are going to change as we go from reactants to products. The law of conservation of matter, however, tells us that matter cannot be created or destroyed. It is a fundamental law in all of science. What this means is that even though the combinations might change, the number of each type of atom must remain the same. We can see here, for instance, that when we decompose mercury oxide, if we heat it up, the mercury and the oxygen will split apart from each other. Oxygen, when it exists by itself, though, exists as what we call a diatomic, meaning that two oxygen molecules are bound together. This is what we refer to as molecular oxygen. It's the same as in the oxygen in the atmosphere and the oxygen we breathe. And so when mercury and oxygen split up, we have one mercury atom and two oxygen atoms. So we can see that what has to happen is that two mercury oxides actually need to break up in order for oxygen to come together. These are the ideas that we're going to explore, and we're going to look at where these numbers come from. Let's look at a simple example of the formation of water. As I mentioned earlier, oxygen is a diatomic, and so the oxygen in our atmosphere exists as O2. Hydrogen is also a diatomic, so it will exist as H2. In order to come together to make water, hydrogen and oxygen will react to form H2O. We look at how many of each atom we have on both sides. We see that we have two hydrogen atoms and two oxygen atoms in our reactants. In our products, we have two hydrogen atoms, but only one oxygen atom. So we say that the oxygen atoms are not balanced. We do not have the same number on both sides of our equation. And so it's tempting to just do this. Can't I just add another O and have H2O2? Then I'll have the same number on both sides. We have to remember that this is a brand new molecule. H2O2 is something completely different. It's not water. What this means is that when we're balancing chemical reactions, we are not allowed to change the formulas of the reactants or products. What we must do is adjust the number of reactants or products that we have. And so, we need two oxygens on the right-hand side of the equation. We can do this by having two water molecules. So if I have two H2Os total, I now have two water molecules. Let's write out the whole equation so we see that very clearly. We can see that if I have one water molecule and two water molecules, now I have a total of two oxygen atoms in my products. However, we can see that this now adjusted our number of hydrogen atoms. We now have 4 hydrogen atoms on our products. So our equation is still not balanced. We don't have the same number of each type of atom on both sides of the equation. So we take care of this by having 2 hydrogen molecules react. This is now a fully balanced equation. We have the same exact number of both type of element on both sides of the equation. That's what you're ultimately trying to do anytime you balance an equation. You need the same number of all types of atoms on both sides of the equation. Let's look at another example. In this example, sodium chloride and magnesium bromide react to form sodium bromide and magnesium chloride. Let's look at another example. In this reaction, sodium chloride and magnesium bromide react to form sodium bromide and magnesium chloride. When we count up each type of atom on both sides, we can see that we are not balanced. Our number of chloride ions is different on both sides of the equation, and so is our number of bromide ions. And so again, it's really tempting to just fix it like this. We can have NaCl2 plus MgBr2 gives us NaBr2 plus MgCl2. However, we learned in the last unit that that is not the formula for when Na and Cl combine or when Na and Br combine. We have to still stick to all of the rules that we learned in the last chapter about how to write chemical formulas. Instead, what we do is we change the number in front of the appropriate molecule. We write a coefficient of 2 NaCls. That now gives us 2 Cls on the reactant side and 2 NaBr, which now give us the 2 Br that we need in our product side. We can see that it also changed our number of Nas on each side. However, we have 2 Nas on the product side and 2 Nas on the reactant side. Therefore, this reaction is now balanced because we have the same number of each type of atom on both sides of our equation. It cannot be stressed enough when balancing equations that once the equation is written, the subscripts cannot be changed. Changing those might violate all the rules that we learned in the last unit, or it might change the compound completely, and we can't do that. So to satisfy our law of conservation of mass, we will add coefficients in front of any molecule that needs it in order to balance the equation. Here, for instance, in the combustion of methane, we see that we've got 1 carbon on the reactant side, 1 on the product side. We have 4 hydrogens on the reactants, 2 in the products, 2 oxygens in the reactants, and 1, 2, 3 in our products. And so the first thing we'll do in this instance is take care of our hydrogens, 4 over here and 2 over here. And so a 2 in front of our waters takes care of the number of hydrogens for us. We now have 4 and 4. And now if we look at our number of oxygens, we've got 2 over here, and we have a total of 2 from our water molecules now, for a total of 4 in our product side, 2 in our reactants. And so a 2 in front of our oxygen on the reactant side takes care of the oxygen for us. We now have a balanced equation with the same number of each type of element on both sides of the equation. These are all of our formal steps in writing a complete balanced chemical equation. First, we'll write the equation using the formulas of our reactants and products. To do that, we will follow the rules that we learned in the last unit. We often want to include the physical states as well: solid, liquid, gas, aqueous, etc. We will then balance the compound with the most elements in the formula first, using our integers as coefficients. We quite often want to save elements on their own for last, like we did with oxygen in the last example. And then we check our answers. We check to see that we have the same number of each type of element on both sides of the equation. If you found you went a little too far, and the coefficients can be simplified by dividing through by a whole number, then you would do so. We do find often with simple equations that a trial and error approach is often faster than going through the systematic steps. In other words, if it looks like you can balance a certain element easily by adding a coefficient, do that, and see what it did to the rest of the equation to see what you might have to fix. Let's look at another example. In this case, we have the decomposition of calcium carbonate in order to form calcium oxide and carbon dioxide. If we count up our numbers of each type of element on both sides, in the reactant side, we have 1 calcium atom in our products, 1 carbon in the reactants, 1 carbon in the products, 3 oxygens in the reactants, and 3 oxygens in the products. So we see that this equation is actually balanced as written. We don't need to add any coefficients. We have the same number of each type of element on both sides already. Let's apply some of the rules that we've looked at to look at this more complicated example. Here we have a combustion reaction. It's the combustion of ethane. We see that oxygen is by itself on the reactant side, so we're going to save that for last because that will be easiest to balance. Hydrogen looks like it might be the element that changed the most. We have 6 on one side and 2 on the other side. And so we're going to go ahead and balance hydrogen first. And so in order to get 6 hydrogens over onto our product side, instead of having just 1 water molecule, we can have 3. Now we have 6 hydrogens over on our product side. However, in doing so, we notice a problem. We can see that now in the product side of the equation, we are always going to have an odd number of oxygen atoms, with 2 here and 3 here. This leads to a problem, because we can see that on the reactant side, with O2, no matter what number we place here for a coefficient, it will always have an even number of oxygen atoms. And so to fix that, we're just going to automatically double our number of water molecules. So now with 6 water molecules here, that will lead us then to even numbers of oxygen. And since we doubled it here, we now have to go ahead and double our number here to take care of the hydrogen atoms. So we now have 12 hydrogens on this side and 12 hydrogens on this side. And so let's recount and see where we're at. We now see that we have 4 carbons on the reactant side, 1 carbon in our products, 12 hydrogens over here, 12 hydrogens over here, 2 oxygens here, a total of 2 and 6 for 8 over on the product side. Now, let's go ahead and take care of our carbon atoms. Again, we have 4 in our reactant side and only 1 in the product side. And so we can change our number of CO2 molecules to 4. Now we have 4 carbons in our product side as well. This leaves everything balanced now except for our oxygens. We see that we now have 8 oxygens in CO2 and another 6 from our water molecules for a total of 14 oxygens in our product side. And so we can take care of that by having 7 O2 molecules in our reactant side. We now have a fully balanced equation with the same number of each type of element on both sides of the equation. When working with polyatomic ions, it's easiest if we treat the entire ion as one thing, rather than counting up all the different elements in the polyatomic ion. In other words, if I'm balancing this equation, I'm going to look at this and say that in the reactant side, I have 1 Na, and I have 1 NO3, I have 1 Ca and 1 CO3, all in my reactant side. In the product side, I have 2 NAs and 1 CO3, and I have 1 Ca and 2 NO3s. And so this is what I mean by treating them all as the same thing. We can see that NO3, since it is a polyatomic ion, stays together on both sides of the equation. And so does CO3, so does our carbonate. Again, this is another reason why it is so important to memorize those polyatomic ions, so that you can recognize that they will stay together during the course of a chemical reaction. And so, in order to balance this, I can see that I'm going to need 2 NAs over on my reactant side, and I'm also going to need 2 NO3s, making this very easy to balance by simply adding a 2 in front of my NaNO3. I now have 2 NAs and 2 NO3s on my reactant side. Now it is a balanced equation. Take a few minutes and practice with these equations. Remember, the overriding rules in balancing equations is that you cannot change any of the subscripts. And so the subscripts that you see here, the 3 on NH3, R2, any of these subscripts cannot change on either side of the equation. Instead, add coefficients in front of the equations in order to come up with the same number of each type of element on each side of the equation. Pause the video now, Practice these, and then restart the video to check your answers. Here are all of the fully balanced equations. If you didn't get them right, go back and check. Count each element on both sides and see where you went wrong. Let's take a quick peek at the combustion reaction. So we start off with this equation looking at our number of carbons maybe. We see that we have 5 carbons in our reactant side and 1 in our product side. So we can fix that by having 5 CO2s. And then we look to our number of hydrogens. We have 10 hydrogens in our reactant side, 2 in our product side. And so we can fix that by having 5 water molecules. And now finally we move to our oxygens. And we see that we have 10 oxygens here and 5 in water for a total of 15 oxygens in our product side. Now, since oxygen is existing as O2 in our reactant side, that means that what we really want to put on our reactant side is 15 halves, or 7.5 oxygens. Now, we know that we can't really have half of an oxygen molecule, but we're going to go ahead and put that there just for now as a placeholder. This will be a fairly common thing that will happen when balancing, especially when looking at combustion reactions. What you do when you reach this point, anytime that you want something and a half oxygen in order to balance it, go ahead and put it there to begin with, and then simply go through and double all of the coefficients in the equation. So that will give us 2 C5H10s, 15 O2s, 10 CO2s, and 10 H2Os. And so we can then see that we have 10 carbons, 20 hydrogens, 20 hydrogens, 30 oxygens, 20 plus 10 for 30 oxygens. And so we have a balanced equation. Balancing equations is going to be something that will be very important for us as we move on to our next topic. So if you're still confused and looking for more help, look at some of the extra practice problems on the website, or come see me, or go to a tutoring session. Any way you do it, though, this is absolutely a skill that we must master for this course.